Swayam Prabha. Digital India. Educated India.
Looking at the problem of the total number of heads being h, where h can take on any one of these values, when you have n tosses of a coin which has an a priori probability that it comes out to be heads with probability p and tails with probability q, which is 1 minus p. So the way you compute this is the following. If you have exactly h heads, then little p is multiplied by itself h times. So the probability of having h heads is p to the power h, and then the rest of them must be 1 minus p, which is q to the power n minus h, because you must have exactly h heads and n minus h will be tails. So this is the probability of a sequence in which you have h heads and the rest tails. But the order in this sequence doesn't matter, because in the two coin case you could have had ht and th and they both counted under one head, one tail. So the order doesn't matter. So this could be either any one of the orders, this or that or that. So all the multiplicative part of the probability is sitting here, but now you have to add all such terms and you have to find out how many there are. How many terms such terms are there? Suppose you want a sequence like this, h, h, t, 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 h, h. And I've got 1, 2, 3, 4, 5, 6, 7, let's say 8 coins, and this is a sequence. What is the probability that this sequence occurred?
Well, it's like
exactly this sequence. What's the probability that it occurred?
Samples case 8 power.
There are 8 coins, and I always look at examples, special cases, and so on. I have 8 coins and it comes out in this sequence. Well, if it's an unfair coin, what's the probability? First of all, the probability that this h occurred first is p. Then you want the probability that this h occurs, and it's an independent coin. So you want p times p. So you have another factor p. And then you want t, which is q. And then you want a t, which is again q, which is again t, which is q, and then this is p, and this is q. So that's equal to 1, 2, 3, 4 p's and 4 q's. So this probability is p to the 4, q to the 4. Because you want this and that and that and that. And the probability is multiplied. But now what we are asking is, we want a total number of heads, h, but we are not saying in what order these heads should appear. They could have all appeared in the first shot, they could have all appeared together or separated by t's and so on. In how many ways can you arrange h heads out of n coins? NCH. N choose h. So this is applying the AND rule and this is applying the OR rule. That's the total probability. Is it completely clear? So in this example, if I ask for the probability that you have 4 heads and 4 tails, this is one possibility. But there are many such possibilities and any one of them would do. So there's an OR rule appearing here. Yeah.
So that formula you've written there, can you say what it implies again?
What?
The formula you've written there, p to the power h into q to the power n minus h. So can you repeat what that implies? I wasn't audible from here.
You'd like to know where it came from?
Oh yes sir. And what it implies?
What it implies is that somewhere you've written down all possible sequences of n letters, in which each letter can be either a little h or a little t. So you've written down all possible words, n letters long, in which the alphabet is just restricted to two outcomes, H and T. Now, out of this, I want to know what's the probability that capital H of them are little h letter and capital N minus H of them are the remaining ones, little t letter. The order in which these heads and tails appear, I am not asking for. I am only saying what's the total probability that you have H heads, the total probability that you have N minus H tails. That's all I am asking for. So I am saying that any one of the outcomes must be made up of a string of this kind in which H of the factors are little p and N minus H of the factors are little q. And then I add up all the number of ways in which I could have realized this sequence, and that's NCH. So this combinatorial factor is very important. Suppose you apply it to the case when you had 4 coins and 2 of them we wanted to know the probability that you have 2 heads. What would you do? You want 2 heads, so you have p squared. You want 2 tails, so you have q squared out of 4 coins. And then you have 4c. So that's the probability. Okay. This is called a binomial distribution. Can you guess why? Mathematicians are very literal-minded people. They give the most direct term for any particular concept, always the most direct terminology. It looks like a term in a binomial expansion of something or the other. We'll come to that in a minute. If I take p plus q to the power n and do the binomial theorem, what is the expansion of p plus q to the power n?
NC0, p to the power n, q to the power 0.
Right. So there is the p to the power n, n, p to the n minus 1, q, plus dot dot dot. The general term in it is just this, where h runs from 0 to n. So if I do that, if I sum Pn of h from h is equal to 0 up to n, this is equal to summation h equal to 0 to n is equal to what? It sums over all possibilities, the probability of all possibilities for h. So the total probability is 1. So this should turn out to be 1. And is it 1? This is also equal to p plus q. So probabilities add up. We haven't left out any event. And each term, each Pn of h is one term in the binomial expansion of p plus q to the power n. Therefore, this distribution in h, the random variable here is h, and that can have n plus 1 possibilities, and the probability of any one of those is given by this formula. And it's therefore the distribution, the probability distribution of the random variable h for a given n, for a given total number of coins. What would you call such a distribution? It's called the binomial distribution. Most obvious terminology, always. We're going to have some fun and games with this. And we'll do that by and by. But let's put some numbers in to see what's happening. Because it's always important in physical sciences to put in numbers to see whether things work out. Okay. We'll take this example of 100 coins. So capital N is a sufficiently large number. It's 100 coins, right? Okay. And let's make life simpler 100 fair coins. Fair means P equal to Q equal to half. What happens for a fair coin? What happens to this? This remains NCH, but this is half to the power h, half to the power n minus h. So it's just 1 over 2 to the power capital N. What is the probability that all 100 are heads?
1 by 2. 1 by 2 power. By CN.
How big is that? Yeah, very small. in the sciences, you never say very small, very big, and so on. Relative to what is the question? Relative to 1. 1 half, they are of the same order of magnitude. It's much, much smaller than unity. How big is this? Roughly in powers of 10, how big is this?
Minus
10 power minus 99, that's a huge, very, very small number. Well, 10 is roughly 8, which is 2 cubed. So about 10 to the minus 30 or so. Really small. Much smaller than Avogadro's number, right? Very, very roughly 10 to the minus 30. What is this? P100 of 0. All tails. Again the same thing, it's the same number, 1 over 2 to the 100. What is this? P100 of 50. So he said that if you toss 100 coins, you're pretty much likely to get 50 heads, 50 tails. We're going to find out if what he said is true or not. So it's 100C50, which is 100 factorial divided by 50 factorial squared 1 over 2 to the power 100. Yeah.
Can we think of this as in the denominator we have this power n, which is the total number of ways in which you can
Yeah.
is to form, and in the numerator the total number of ways in which you can arrange them to form h heads, no matter how you can think of it like that.
Well, we did precisely that. We found the number of ways in which you can get a particular edge. We multiplied by that factor. That was the binomial factor NCH. That's exactly what we did. So there's no numerator denominator here. There's a multiplicative factor coming from the total probability of any one possibility for that event, multiplied by the number of ways in which that event can be realized. Right? So the probability of exactly 50 heads is this number. How big do you think this is? How do you calculate this number? 100 factorial is a huge thing. You can cancel out 150 factorial and get in the numerator 51 to 100 product, but there's a 50 factorial in the denominator. How big do you think this is? That's true. It's something into 10 to the minus 30. But remember, the total probability of all outcomes here has got to add up to 1. But you're starting out at one end at 10 to the minus 30, at the other end at 10 to the minus 30. By the way, what's the probability that n minus 1 times you get head and once you get tail? You get NC or you get NC1. What's NC1? N itself. So we know immediately of 99, for instance, is equal to 100 to the 100. That's not doing very much. It's taking you from 10 to the minus 30 to 10 to the minus 28, which is pretty small still. So it's starting off very slow. We expect it will build up near the middle because 50-50 is very likely, as he says. But I'd like to know how likely is likely. Remember, we're dealing with numbers like 10 to the minus 30 here. How will you calculate this number? This immediately leads you to non-trivial matters. If you try doing it on a pocket calculator, for instance, I don't know if they're still around, or your computer calculator, etc., it will show an error message because the thing will take only up to 10 to the 99. This is much bigger than that. 100 factorial is much bigger than 10 to the minus 10 to the 99. At about 67 or 70 factorial, the computer will stop working unless you do something clever. Yeah, that's a special case. We want a general rule by which you can compute such large numbers and such small numbers. Okay. I urge you to do this by whatever means. I'm going to show you a trick for doing this, but I'm going to...
Well, so this is increasing by 100.
Yeah, but the next term will increase by n times n minus 1, so there will be 100 times 99, and the next one will have 100 times 99 times 98, but divided by 3 factorial and so on.
Do you want the exact answer or like the order of magnitude?
I want the order of magnitude. Give me to 1 decimal, 2 decimal places, for instance, what the probability is. You need an estimate for the factorial of large numbers. And the factorial of large numbers gets very rapidly very large. For very large n, it will go like n to the power n, just enormous. So what will happen is that this factor will compensate for this factor and make this whole answer quite realizable. And the answer turns out to be about 8%. So this will turn out, and you will see why, is approximately 0.08, which I think is pretty large. Compared to 10 to the minus 30, 8% is very, very large in between. So you see, this factor starts dominating when you have large numbers. This is the reason why all the air in this room doesn't condense in one corner and suffocate the rest of us. But we'll work out that probability in a minute when this is going to happen. It's also the reason why when you park a car, it's easier to take it out into the traffic than to put it into the parking spot. And I'm making these mysterious statements, but you'll see why, in a very logical way, why this is so. But first, let me give you a formula for the factorial of large numbers without proving it. Proving it requires integral calculus, which you haven't studied yet. Have you studied integral calculus yet? Yes? Then later on I will mention, because that's a digressionary remark, what the factorial, where the formula comes from. And this is a very important formula. It's called Stirling's formula. It's generally called the Stirling approximation, but it's such a good approximation that I would like to call it a formula, which it actually is in a certain sense. And it says that n factorial is equal to n raised to the power n, because you can take n factorial and write it times n minus 1 times n minus 2 right up to 1, and you pull out an n from each of the brackets and you get n to the n. But it's too large because you're going from n, you're going to 1, you're decreasing. So this is an increasing factor, therefore you got to compensate by something decreasing. And what it is, the correct answer is e to the minus n. Does everyone know what e is? What's the value of e? 2.718, 1828, etc. Is it rational or irrational? Irrational. What does that mean? What does it imply for the decimal expansion of e? Non-recurring, non-terminating. Okay? Goes on forever. Can you predict what the next term is, or it's completely random?
You can predict it.
You can predict it. You can compute it. We'll come to this. What about pi? Okay, we will come to computing pi and e and so on. But for the moment, e is of the order of 2.71828, goes on forever, whatever. This, it turns out, overcompensates. So there's one more factor which is square root of 2 pi n, multiplying it, times 1 plus a correction which is of order 1 over 12n plus a correction which is of order n squared. So this means there are terms of order n squared, 1 over n squared. This means there are terms of proportional to 1 over n squared, 1 over n cubed, 1 over n4, all the way getting smaller and smaller. The leading correction is this. For most practical purposes, this is enough. And that will give you your 0.08, etc. So I urge you to do the following. Take Stirling's formula, forget all these terms, use this for n factorial, for 100 factorial and for 50 factorial, and you will end up with that answer. Yeah. Multiplying. Yeah, so I sort of gave a hand-waving argument saying that n factorial is like n factors, n times n minus 1, n minus 2 up to 1. I pull out an n from each bracket, I get n to the n. But you got terms which go like 1 minus things which decrease. So therefore, there's got to be a decreasing factor which turns out to be e to the minus n. But that turns out to overcompensate, so you again got an increase, and that's going like square root of n. So I haven't derived this formula. There's a very way of deriving it using integral calculus, which I have not talked about. Yeah, 1 second. Yeah, this O stands for of the order of. Pardon me? No, it's not a geometric progression. It's not 1 over n squared plus 1 over n cubed plus etc. It's got some numbers as coefficients.
So could we explain exactly what of the order?
It means if you divide by this number and divide it by 1 over n squared, you get a coefficient of the order of finite of 1. There's a whole little digression on what's meant by little o and capital O notation, which I don't want to get into here, except to tell you that the correction will go like this. But you see, although I called it an approximation, the reason I like to call it a formula is because if you take the first approximation to this formula, you already get an extremely accurate answer. You ignore all these things and you have this. N factorial is this. What's the smallest number to which you can apply this? It depends on the accuracy you want, right? So this is n factorial, so the factorial of positive integers. If I apply to 1, what happens? Smallest positive integer. What happens if I apply to 1? So I get 1. Is that 1 to the power 1 e to the minus 1 root of 2 pi? So the question asked is e approximately root 2 pi? It's not equal to, they are very different numbers altogether. What would you say? I've given you enough data to tell me, is this true or not? It's actually true to this accuracy. It's actually true up to neglecting 1 over 12, which is 92% accuracy. So here's a formula which is supposed to be an approximation. At n equal to 1, it's already giving you an answer which is 92% right. At n equal to 10, it gives you an answer of the order of 1%, correct, 1 over 120. When n is 100, it's much more accurate. And what happens when n is Avogadro's number? Which is where you're going to use it in heat and thermodynamics and kinetic theory and so on. You use this approximation for the factorial of Avogadro's number. And you can forget about these corrections because this is of order 1, this is of order 10 to the minus 24. So it's not even an approximation. It's as exact as you can ever get. Okay. So it's a remarkable formula here. And if you use that, you can compute this number. And if I plot this, you're going to get an interesting distribution. If I plot it in the fair coin case, for instance, so this would be all tails, n equal to p, and this will be n equal to h. You got very small thing going here, and then it slightly rises, and then it rises more, and so on, till it rises over. You get a kind of bell curve, but it's a distribution in discrete variable capital H, so it's not a curve, but more like a histogram. But when it's large, it looks like a closed curve, like a bell curve. Yeah. So I want you to calculate, and this is a good exercise. Take 100 fair coins and calculate the probability, not that you had 50 heads and 50 tails, for which we got this answer here, but the probability that you get somewhere between 45 and 55 heads. 49-51 is a pretty close approximation to 50-50. 48-52 is pretty close, etc. So I want you to numerically compute using Stirling's formula the actual probability, total probability, that you get either 45 heads and 55 tails, or 46 heads and 54 tails, right up to 55 heads and 45 tails. Add up those probabilities, and you discover the answer is very close to 1. So what it's telling you is that this probability distribution, which I've imperfectly drawn here, is extremely tiny here, and boom, it goes up and comes down very quickly. Then the question is, what should be the width of this curve? Where is the probability significant? And that's where the standard deviation comes in. That's the import of the standard deviation. Most of the probability mass is in there. I think I've exceeded my time. We'll stop here today, but I have one final question, and that's the following. I go back to my unfair coin with probability P of heads, and I ask the following slightly different question. I toss this coin, and I continue to toss till I get a head, and then I stop. What's the probability that I get a head for the first time in the nth toss? Unfair coin. Fair coin, it's a trivial problem. But we'll do the unfair coin first and then generalize, use P equal to half. What's the probability that I get? Now, what's the random variable? First of all, what's the random variable in this problem? When you do any probability problem, you should first identify what's the random variable and what are the possible values it can take, which is called the sample space. In this question, I take an unfair coin and keep tossing it till I hit a head, and then I stop the experiment. And I record the toss number at which I got the head for the first time. So what are the possible values of this n? It could have been 1, 2, 3, and then what's n? Can be any number. Can it go up to infinity? Yes, indeed. It can go back for millions and millions of processes. Not very probable, but it can happen. So what's the probability that you get a head for the first time on exactly the nth toss?
On the nth toss, right?
Yes, that's what we're asking.
So wouldn't that be 1 minus 1 by 2 power n?
Let me call it P of n. P is a bad symbol to use. I've already used capital P. So let me be fancy and call it rho of n. Not very good at writing Greek symbols. That's the probability that on the nth toss, you get head for the first time. You've not seen heads before that. Everything before that is a tail. And it's an unfair coin. So it should have become tail, 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 head. This is a head for the first time in the fifth toss. What's the probability of this happening? Why times C1. So what's this probability? And what are the values of n?
1
All the way to infinity. You could continue to keep getting bad luck. Can happen. Why are we not getting binomial coefficient? Why should we get a binomial coefficient? I've specified the sequence. I've specified this has got to be so. There's no arbitrariness here. It's one sequence. I must get t's all the way up to the nth toss, and the nth toss I should get h. There's only one sequence in which it can happen. So we have it. You have q occurring n minus 1 times, and then finally there must be a p. The sample space is the sample space of the random variable. The random variable is n, which is the number of the toss at which you got the correct head for the first time. So this random variable is not the number of heads or anything like that. This random variable is that particular toss number at which you got head for the first time. Why 1 over n? No, they're not all equally probable. All the tosses are independent of each other. Each time I toss the coin, the probability that I get head is little p and tail is little q. But I want a head for the first time. I don't want to see it for the first n minus 1 tosses. I want to see it in the nth toss. And this n itself can take values 1, 2, 3, 4 all the way. The proof of the pudding is the total probability that you get a head at all should be 1 eventually. Right? So you want this to be true. You want summation n equal to 1 to infinity rho of n should be equal to 1, because getting a head is a definite event. Is this true, by the way? Is this true? P is a factor which appears in every term, so it comes out of the summation, and then you have to sum from n equal to 1 to infinity q power n minus 1. What's the value of that sum? It's a geometric series. 1 plus q squared, etc. Q is less than 1, so it's a geometric series in which the common ratio is less than 1. So the sum will have a finite answer. What is the first term? 1. And what's the formula for the sum of a geometric series? A over 1 minus r. A is 1 in this problem. So what does this reduce to? So the probability is normalized to unity as we put it. The total probability is 1. So it's a genuine probability distribution, and it has this funny behavior. What would you call this distribution in n? It's not a binomial distribution. There's no binomial coefficient. What would you call this distribution? You got a geometric series. Don't be tentative. It's called a geometric distribution. Like I said, there's always the direct name. It's the geometric distribution. What's the average number of tosses I have to perform in order to get head for the first time? How would you do that? How would you find the average value of n? That's a trickier question. I'll use these curly angular brackets for average or whatever is inside the bracket. I don't want to use the bar, overhead bar, because overhead bar cannot extend long enough. I may want the average of a very complicated quantity. It will be an arithmetico-geometric progression. Not divided by n. You go where it goes takes you. I mean, you have to find the arithmetico-geometric distribution. So this, the actual formula for this is equal to summation n times rho of n divided by summation rho of n. The weighted sum over n. That's the meaning of the average value of n. So you will get, in the denominator you get the normalization 1, but in the numerator you get an arithmetico-geometric series, and you have to sum that, for which you already know the way of doing it. Okay. I'll show you a much quicker way of finding the averages by inspection, by looking at it immediately a little later. But you see, already you are beginning to see that one distribution is leading to another, which is leading to another, and so on and so forth. What do you think is the answer if you had a fair coin? What do you think is the average number of tosses you need before you get head for the first time in a fair coin? Should be 2. That's good intuition. It's 2. And what would it be for general P? Look at always the limiting cases. What happens if the probability of a head is vanishingly small? How many tosses would you have to perform? It would have to diverge. It would become infinite, right? And what happens if you had a coin which has got only heads? It does it in 1. So it runs between 1 and infinity. The correct answer in this case is 2. In fact, this term, this will turn out, a little bit of algebra, it will turn out to be 1 over. And when P is a half, this is indeed 2 as he put it, as he said. So I'll stop here now and we'll resume from this point. Okay. Meanwhile, I want you to calculate the following quantity as an exercise. We'll take all the gas in this room and it's in a volume V, and there are n molecules of air, so the number is n. I take a snapshot and freeze all the molecules, look at it at one particular instant of time, and they're spread out all over the place at random. And I have a little box here of volume little v. The capital V is the total volume, and I have a box here, a sub-volume little v. A little 1 cubic meter box in one corner of the room. I have a total number of molecules n. And I want to know what is the probability that in this little v there are n molecules at any instant of time. I freeze the particles at some instant of time hypothetically, and I say, what's the probability that this sub-volume V, which is much smaller than capital V, contains exactly n molecules? What is the sample space of this number n? Well, it could be 0, it could be 1, it could be 2, it could go up to capital N. If it goes up to capital N, that's bad news for the rest of us, because if you're outside the box, you'll choke. So I'm trying to get you to compute the probability that all the air in this room will spontaneously condense in 1 small cubic meter somewhere in the corner of the room and kill the rest of us. We need to find out for survival, right? So I want you to compute this. N runs over 0, 1, 2, up to capital N. The answer will be a function of little v, it will be a function of capital V, it will be a function of capital N. But you need to find out what's this probability. And it's just common sense, nothing more is needed than that. We made enough approximations and assumptions here, it's just common sense. Of course, you appreciate the fact that if I actually did this experiment, that number n is widely fluctuating because molecules going in and out of that little hypothetical box all the time.